All right, we are finally ready to start using Laplace transforms to solve differential equations. For now, it's important to recognize that we have this library that we built up of Laplace transforms of certain things, and we know that we can go backwards. Additionally, we have this new thing, is that the Laplace transform of the derivative of something is minus something at t equals 0 plus s times the Laplace transform of the function without the derivative. This, combined with the other things, are going to allow us to solve differential equations. It's also important to recognize that we can use this recursively in that it says the Laplace transform of the derivative of something is going to give us this result. So, for example, if I want to take the Laplace transform of the second derivative, well, that's the derivative of the first derivative. So that's going to be minus y prime of 0 plus s times the Laplace transform of y prime. And now I can use the previous formula to write that in terms of the Laplace transform of y. So we end up with Laplace transform of the second derivative is minus y prime of 0 minus s y of 0 plus s squared times the Laplace transform of y. And we get that by multiplying that s through. So I'm just rewriting this formula. Then could be used to find the third, fourth, fifth, and further derivatives. And notice this means that I can take a Laplace transform of a differential equation and write everything in terms of the Laplace transform of y. Now it becomes an algebra problem to get things from there. So, what do we know? Given an ODE, and we're assuming that it's a linear differential equation, we're going to take the Laplace transform of everything. We're going to take that result and just keep expanding as much as possible until we can't expand it anymore. Then we're going to do the algebra to solve for the Laplace transform of the function we're looking at. Once we do that, we can rewrite the Laplace transform and we're going to do it in a way so that we can go backwards in terms of finding the inverse Laplace transform. And so when we have that, we can figure out what our function is. And it's important to note here, this is Calc 2. Step 2 is basically algebra. Step 3 is algebra. Step 4 is algebra. But we should note that there's some experience involved there. You have to get a feel for that. Again, this is something you just got to sit down and do. So you need to get a feel for this. And that is just a matter of going backwards once you've done all the hard work. Okay. So, and as you go through and do everything, you should always have this table in the back of your mind, thinking about how you're going to use it. So, for example, if you were asked to find the Laplace transform of t times e to the 3t, you should be able to recognize that that's 1 over the quantity s minus 3 squared. And given this, you should be able to go backwards to get t e to the 3t. So if you're asked to solve for y, and you have this differential equation, by the way, note you could just do an integral in this case and go through and work everything out. You can do integration by parts. It's going to be a mess. But if you do the Laplace transform, we know the left-hand side is going to be minus y of 0 plus s Laplace transform of y. And the right-hand side is going to be that. So we know this is equal to 4. And that's what we want. So we're going to do some algebra now. Add 4 to both sides. Divide through by the s. And now in terms of Laplace transform, you should immediately look and see, recognize the Laplace transform of 4 is 4 over s. That's going to be a problem. But if we stop and look at that separately, you should recognize that you can use partial fractions. And so now how do we solve that? Well, if we multiply both sides by s, and s minus 3 squared, so multiply that through. We get this expression. We basically factor out the things from the denominators. If I let s equal 0, I get 1 equals 9a, so a is 1/9. Let s equal 3, so I get 1 equals 0, 0, 3c, so c is 1/3. And if I let s equal 1, I'm going to get 1 equals, so that's 1 minus 3 is minus 2 squared, is 4a. This is going to be 1 minus 3 is minus 2 times 1, so I'll get minus 2b plus c. See, a is 4/9, or a is 1/9, so 4 times that, minus 2b, and c is 1/3. Let me write that as 3/9. So I get 1 is 7/9 minus 2b. So 2b is 7/9 minus 1, it's minus 2/9. So b is minus 1/9. So that means that my Laplace transform, we said, was a over s. A is 1/9 plus b over s minus 3. We said b is minus 1/9. And then c was 1/3. So I get this expression, and this is going to be 1/9 times the Laplace transform of 1 minus 1/9 times the Laplace transform of e to the 3t plus 1/3. And we've already seen that this is Laplace transform of t e to the 3t. So my y is going to be 1/9 minus 1/9 e to the 3t plus 1/3. Oops, I forgot something. T e to the 3t, so be very careful here when I forget. We just solved for this expression, and that's what I used. But I need to use this to get the Laplace transform of y. So I forgot the 4 over s. So this is 4 times 1 over s. So this is 4 times Laplace transform of 1. Which means means then this is plus 4. Don't worry about simplifying this, just leave it like that. That's perfectly fine. And that's just algebra. And we've already seen that this term simplification doesn't really mean what we think it means. What if we had the second derivative is t e to the 3t, where y of 0 is 4 and y prime of 0 is minus 2. So taking the Laplace transform of both sides, I get this, and we already know that this is going to be 1 over s minus 3 squared. And we've found that this is minus y prime of 0 minus s y of 0 plus s squared times the Laplace transform of y. It's 1 over s minus 3 squared. So I'm going to try to isolate the Laplace transform of y. So s squared times the Laplace transform of y. It's going to be 1 over s minus 3 squared. Y prime is minus 2. So that's a minus 2 is a plus 2. So I subtract 2. Y0 is 4, so that's a minus 4s. So I add 4s to both sides. Now I divide both sides by s squared. So this becomes minus 2 over s squared. 4s over s squared becomes 4 over s. And now I don't know how to deal with that. So I would use partial fractions. So a over s plus b over s squared plus c over s minus 3 plus d over s minus 3 squared. All right, I'm not going to go through and show you how to figure out what a, b, c, d are, simply because you should be able to do this by now, and it's very tedious. But when it's all said and done, for A, I got 2/27. For B, I got 1/9. And for C, I got minus 2/27. And then for D, I got positive 1/9. And then I got to include the minus 2 over s squared plus 4 over s. Now when I do the inverse Laplace transform, 2 over 27, the Laplace transform of 1 is 1 over s. Laplace transform of t is 1 over s squared. Laplace transform of e to the 3t is 1 over s minus 3, and we've already seen Laplace transform of t e to the 3t is 1 over s minus 3 squared. Laplace transform of t is 1 over s squared. And Laplace transform of 1 is 1 over s. So there's my solution. And by the way, notice, looking at this, my initial conditions were automatically compensated for, and there's no constants from integration anywhere. They immediately get thrown in, and I immediately solve this for these initial conditions, and I get that basically for free. This was just looking stuff up in a table, working with a table, algebra. This is a lot of algebra. And then once I get to here, I'm just playing games with the table. Okay. And again, just leave your solution like this. You don't have to simplify that, whatever that means. This is just easier to deal with.